Hi everyone, welcome back. In this session, we're going to see about the depth-bound DFS and depth-first iterative deepening. So these two algorithms are the remaining two algorithms of a state space search. In our last session, we have seen the basic algorithms of the state space search, that are DFS and BFS. So these two algorithms are the basic algorithms for the state space search, and also we have seen the performance evaluation of the depth first search and breadth first search. So this is the performance evaluation. For DFS, the time complexity is the exponential, and also the space complexity is the linear. For BFS, whereas for BFS, both time and space complexity are exponential, whereas in terms of completeness and quality of solution, DFS will not complete the what if the particular graph is an infinite graph, then this particular DFS is not complete, because this DFS will be deviating from the goal node. So and it will go into the infinite path, whereas in BFS it will guaranteely find the solution, and it will also give the shortest path after some time of the being executed. So for executing, it is taking the higher time, but guaranteely it will give the solution. So by comparing these two algorithms and their performance evaluation, we can see the DFS is having the space complexity that is low space complexity. By comparing these two algorithms, DFS and BFS, we can clearly see that the DFS is having the linear space complexity, that is, it is taking the less space to execute the algorithm. And also this BFS, it will guaranteely give the solution, and also whatever the solution it is returning, it is an shortest path, that is nothing but it is an optimal solution. So keeping these things into mind, we have to make sure we will explore for the other algorithms which they will exhibit it having a lower space complexity like DFS, and also it should return the optimal path, or it should be complete like a BFS. The next algorithms we are going to see is depth-bound DFS and depth-first iterative deepening. These two algorithms will be using DFS, and also this DFS, whatever the drawback which we have seen in DFS, that is infinite path. This particular infinite path we will try to overcome this particular disadvantage of DFS. The first algorithm we are going to see here is depth-bound DFS. It is also called as depth limited search. This particular algorithm will use DFS. So this particular algorithm is having whatever the DFS, whatever the disadvantages we are having in the DFS, that is infinite path, so it was eradicated. So by making whatever the nodes, if that particular node is going beyond the depth limit, so at the nodes that are present at the depth limit will treat their children as a null child. So at that particular place, that particular algorithm, so it will try to say that particular node is not having any childs. So like that, so that particular algorithm is executed, and we will be having some value. So like it was treated like a finite graph, although it is an infinite problem, so we will treat it as a finite graph. This depth limit search will be having two different types of exit conditions. So first one is a standard failure condition. In this particular condition, whatever the goal node we are searching for, that particular goal node will be not presenting in our system. So in our problem, so that particular goal node is not there. So this particular DBDFS, so it will execute the graph within the depth limit. So in that particular depth limit, so this particular graph node is not there, then it will be giving, so the goal node is not present in our problem. So there can be two cases. The two cases are the standard failure value, so in which the particular problem doesn't have any solution, that means our goal node is not present in the solution itself. And the second exit condition is the cutoff failure condition. So it defines that no solution is present until the depth limit. So whatever the limit we have taken, so at that particular limit we don't have any solution. So like that we will going to return. So coming to advantages and disadvantages of DBDFS, this particular depth limit search is an memory efficient. So as has taken it from the depth first search, just we are applying the depth first search for that particular limited of the particular graph. So it is same as a DFS, so that this particular DBDFS will be having the space efficiency like the DFS. So coming to disadvantages, this particular DBDFS or depth limit search, so it is not completed. That means it is incomplete. So if the particular goal node is present after the depth limit, so as per our algorithm, so it will search only in the depth limit area. After searching, it will say that particular problem is not having any solution, but this particular solution is present for the problem, but it was presented after the depth limit. So at that particular conditions, this DBDFS will not return the solution, and also it will say there is no solution present. So because of this, we can say this particular algorithm is having the incomplete solution. And also this particular solution is not going to give the optimal solution. That is, so this particular algorithm is going to execute DFS. So as per DFS, we are going to search the particular problem, and whenever the particular solution is having more than one solutions, so DBDFS will be returning the whatever the solution it has encountered first. So after whatever the first solution it got, so at that particular instance, DFS will exit and it will give the path for that particular whatever the DBDFS it has found out the solution. So at that particular goal node it will give. So if that particular goal node is having more than one or more solutions, so at that particular time, so it will give only the first, whatever the first solution it has encountered. So maybe there can be an optimal solution at the last, whatever the other solutions in that particular other solution, we can have some optimal solution. So because of that condition, it going to miss out the optimal path, and it will give the whatever the first encountered solution it has got. So it will give that particular first encountered solution. So how this particular DBDFS is going to work on a graph. So for example, I have taken a graph like this. So tree-like problem. So in this particular graph, this S is the starting state and the J is the goal state. Now let us see how this particular depth bound DFS or depth limited search is going to applied on an example graph. So in this example graph, we can see, so S is the starting node and J is the goal node. So we have to, and the depth limit which predefined depth limit value is 2. So for this problem, so whatever the nodes that are present after the level 2, so these nodes will be ignored by their parents, that is C. So for initially C is having two nodes or two childs, that is E and F. So after depth limit has came, so this particular C is going to act that it does not have any childs. So and this particular C has a leaf node. So first I will start from S, and this particular S is going to be checked. We will just apply the DFS on this particular, so whatever the graph we are having, so this particular graph we are going to apply DFS. So first S node, we will pick the S node. So this particular S node will be checked for the goal node. S node is not a goal node. So we will apply move gen function on S. So after applying move gen function on S, A and B will be the output of that particular move gen of S. So then I will having, so A and B will be added to the open. So after A and B are added to open, so I will take the values from the left to right point of view. So after S, in open I am having A and B. Among the open, A and B I am going to select A. So after selecting A, so again A is checked for the goal test. So A is not a goal node, so move gen function, we will apply move gen function on A. So after applying move gen function on A, so C and D will be the input, and this particular C and D are added to the first of the open. So either I will go to C or D, not the D. So that means I'm going to compare both. So I will again compare the whatever the nodes. So C, D. So after this A, I'm going to select D, C. After checking upon C, I will apply move gen function on C. So after applying move gen function on C, so initially actually what is going to happen is E and F will be returned as output. So but we will check the depth limit of that particular nodes. So after this particular depth limit of E is 3 and also F is 3, so these two is ignored and they will not be added to the open. So after C is checked, so D and B are having in the open. So this D is the leftmost value, so D is picked and D is again checked for the goal test. So particular G is not having the, so whatever the G, so that particular G is returned as an move gen function. So after this move gen function, again this G depth limit will be checked. After checking the depth limit, so D will be removed. So I will check B. So B is not a goal node, so I will apply move gen function on B. So I will get I and J as the output for the move gen function. So this particular I and J, whatever the depth limit is checked, the depth limit is 2, so it is within the depth limit. So these two I and J are added to the open. So after this particular one, I and J will be in the open. So I will be the leftmost one. So I will again check I value. So I is not a goal node. So I will apply move gen function on I. So after applying move gen function on I, H will be the output for the move gen function on I. So this particular H, we will check whether what is the depth limit. So after applying whatever the depth limit, the depth limit of H is 3, so this particular H is not added to the open. So after this one, so only J will be in the open. So this particular J will be picked and it will be tested. So here the goal test condition will be true because J is the goal node. So after finding out, I am going to give the whatever the path by using reconstruct path function, I will give the path from S. So that is S to B and B to J. So this is the depth limit search or depth bound DFS on an graph. Our next algorithm is a depth first iterative deepening. So this it is also called as DFID. So and also it is also called iterative deepening depth first search. So all these names will be the same algorithm. This particular algorithm is will be working again. This algorithm also works on DFS. So whatever the depth limit search we have taken, so in this particular depth limit search there will be some predetermined value that is called as depth limit. So we will take that particular depth limit as a consideration and we will apply DFS on that particular graph. So by using this depth bound DFS, so we will be having a disadvantage of, because it is will not be so it will be incomplete. Our next algorithm is depth first iterative deepening. So this particular algorithm is also known as iterative deepening DFS. So it is denoted by DFID. So this particular algorithm is the combination of both DFS and BFS. So this particular algorithm also will be working on DFS. So mainly working on DFS. That particular DFS will be applied on the whatever the problem we are going to get. So for whatever the this particular DFID and whatever the DBDFS, what is the main difference is, in DBDFS we are having a disadvantage of incompleteness. So because if any goal node is present after the depth limit, so that particular algorithm is not going to find that particular solution. So that's why this particular DFID, so this particular DFID algorithm is going to work on that particular depth limit, so that this particular depth limit, initially they are going to take this particular depth limit as 0. So after that taking depth limit as 0, they will apply on the whatever the graph they are going to get on that particular graph they are going to apply. So after that particular whatever the applied, so after applying DFS on that particular iterative 0, so that is depth limit 0, so then So it will check whether the goal node has reached. If that particular goal node is not reached, then it is going to increment the depth limit to 1. So after incrementing the depth limit to 1, again this particular graph will be having some subgraph until level 1. So it will take that particular graph and it is going to apply DFS on that particular graph. So after applying that DFS on that particular graph, again it is going to check so whether that particular goal node has reached. So if that particular goal node has reached, then it will stop right there, or it will continue until the until our total whatever the graph is there or whatever the problem is there, that particular problem space will be searched. So like it will keep on incrementing the depth limit from 0, 1 up to so on until that particular goal node has reached. Disadvantages we are getting from the DBDFS, it was eradicated in this DFID, and also what these the advantage is it combines both DFS and BFS, and this particular algorithm has a fast search, and also it is having the memory efficient because we are applying DFS. And coming to the disadvantage, the main disadvantages in this particular DFID is we are going to search this particular whatever the algorithm we have applied on depth limit 0, then we are going to apply this particular depth limit 1. So again this particular algorithm will be repetitively applied on whatever the nodes we are already checked. So that means we are going to repetitively checking that particular algorithm for the goal test and everything, so will be checked repetitively until our goal node has reached. So whatever the previous stage we are having, in this particular previous stage we are having, so we are going to check everything again after increasing the depth limit to next phase. So again it will going to check whatever the nodes that are present in the previous stage plus whatever the depth limit we have increased. So like that we are having some wastage of time complexity will be there. Now we are going to see how this DFID will work on the whatever the graph we have taken. So in the particular graph we are going to apply this DFID. First we are going to take this particular depth limit as 0. So depth limit will be taken as 0. So after taking this particular depth limit as 0, we are going to construct whatever the graph we are going to get. So here, so this particular level 0 is the depth limit 0. So whatever the nodes that are present in this particular depth limit 0, they will be taken. So the node that are present in depth limit 0 is only S. So next I am going to apply this DFS on this particular S, and I'm going to get this goal node will not be found in this particular depth limit 0. Then so at that particular first iteration, so my output will be only S will be the visited, then only S will be visited. So after going to from this one, I'm going to increase that particular depth limit from 0 to 1. So after increasing that particular depth limit to 0 to 1, so the graph I'm going to get is S, A and B. So I'm going to apply DFS on this particular graph. So first S will be visited and S will be checked. After that I'm going to A, and A will be checked, and after that B will be checked. So after completing B, so the open will be empty, and we will come to a conclusion that particular goal node is not present in the depth limit 1. So after that again I'm going to increase the depth limit from 1 to 2. So here we are going to take J as an goal node. So after increasing the depth limit from 1 to 2, then the graph I'm going to get is, so after A I'm going to have C and D, and after B I and J. So this is the graph I'm going to get after depth limit 2. So I'm going to apply DFS. First S will be checked. So after that one A will be checked. So after A I'm going to check C. After C I'm going to check this particular D. So D is checked. So after that one, So after D, I'm going to check B. After B, I will be checked. After I, J will be checked. If my particular goal node is J, then this particular J will be found in the third iteration. So this particular third iteration itself, I am going to find the J, goal node J. So for the same graph, if I have taken G as an goal node, then so this particular graph is going to return that particular goal node at the fourth iteration, that is depth limit of 3. So first I will start from depth limit 0, S will be checked. So S is not a goal node. So and after S depth limit will be reaching the depth limit 1. So I will increase the depth limit to 1. After increasing the depth limit to 1, again I am going to check S, A, D. After SAB will be checked. So after SAB, so our goal node is not reached again, so we will increase the depth limit to 2. So after increasing the depth limit to 2, first I will start from S. After S, A. After A, C. So after C, I am going to D. So after D, I will go to B, and after B, I will go to I. After I will go to J. So here our goal node G was not found. So again I am going to increase the depth limit to 3. After increasing the depth limit to 3, so whatever the graph we are earlier, whatever the graph, so total graph, this will come under this particular depth limit 3. So after this, in this particular depth limit 3, I am going to apply. So first S will be checked. So S is not a goal node. So A and B are added to the open. So after A and B are added to open, I will check A. A is not a goal node. So whatever the childs of A, C and D are added to open. So first among C and D, I am going to check C. So after checking C, C is not a goal node. So whatever the children of C, they are added to open. So E and F will be added to open. So among E and F, first I will go for E. So this particular E is checked first. So E is not a goal node. So again, so I will check the next node, whatever the I will check whatever the next node that is present in the open, that is F. So after checking F, I will be going from F to D. So after D is not a goal node. So whatever the child of D, so that particular child G is be getting as an output for motion function. So this particular G, so whatever the G we are having, this particular G, so we will check for the goal test condition. Now G is a goal node, so this particular G is found. So the path which is going to be returning is S to A and A to D and D to G. So if that particular the goal node is G, then we are going to find out the goal node G in the fourth iteration. So iteration 4, that is depth limit of 3. Coming to the performance evaluation of this depth first iterative deepening. So this particular algorithm, we can say it is infinite, because we are until the goal node is found, we are going to increase the depth limit and we are going to keep on searching for the goal node. So by taking these considerations, we can say this particular DFID is complete. And coming to time complexity, that particular time complexity is an exponential like the DFS. So exponential will be having the worst time complexity, that is order of, so B power D. So here B is the branching factor and D is the depth limit, depth of that particular tree. Whatever the depth limit is there at that particular depth limit, that depth limit is the D. So here the time complexity of this DFID is an exponential, so like DFS. And coming to space complexity, so it will be the order of B into D, and we can say it is an linear, so like DFS. And coming to whatever the optimal or quality of solution, so whether we are going to get any optimal path or not. So this particular DFID is then optimal. So if the particular path cost is a non-decreasing function of the depth of the node, so that particular whatever the path cost is there, that particular path cost has to be an so non-decreasing function, and that means it has to be an increasing order. So as it is compared to the depth of the node. So if this is the performance evaluation of the DFID. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.